So thanks a lot for your interest in coming here today for these lectures, for this series of lectures on geometric data analysis. Okay, so I'm Jean Fédy. I'm researcher at INRIA now. I'm going to say a few words about myself. Yeah. Okay, so as you've seen, the lectures will take place here, so in the Faculté de Médecine. So 7 lectures of 3 hours. And I know that, okay, it's very far away from Saclay. The room is not super large, mostly because I expect that in 2 weeks we're going to be 20. So we should be able to fit all here. But okay, because I don't want to put too many constraints on you and I want this course to be easy to validate, I'm going to put everything online. Okay, if you go on my website, basically you Google Jean Fédy, you go in the teaching tab, and you're going to find everything that's important for the class. Okay, so with respect to the validation, also going to be very easy. So in lecture 7, at the end, I'm going to make a short quiz, like maybe 10, maybe 20 questions. Very easy I mean, basically just so that you all get 10. And then I can grade projects, like, honestly. Okay, and then a project. And this, okay, so I don't know what happens in other classes, but personally, I really like what Xavier Pennec was doing in his class on medical image analysis. So it's going to be in the same spirit. So I'm going to give you a list of 30 interesting papers. You can obviously come up with papers that you like. And yeah, try to do it yourself alone or in pairs of 2. I think a pair of 2 is the best format. And yeah, just write a short report on the paper, like 4-8 pages. I'm going to send you a template. And maybe implement things, try to show that you have understood something, and then we're going to make, depending on how many you are, probably short one-on-one interviews, in my office, something like that, as an oral presentation, because we don't have time to have you all and organize a mini symposium. Maybe if you're 10, that's what we're going to do. Okay. So first word maybe is that you've seen that we are not in the INS Paris-Saclay, we are not in the ENS, we are not in Polytechnique, we are in the Faculté de Médecine. Okay, I don't know, maybe that's the first time for you in this kind of environment. And there are 2 reasons for this. So the first one is that, okay, this lecture is really motivated by medical applications. So it's going to be mostly general mathematics, not a lot of I mean, if you're not interested in healthcare, that's fine. But all the tools that I'm going to present these months are tied to real-life applications. Okay, and I think that you cannot do real-life applications if you stay in your office, if you stay in front of your computer, if you look at a big Excel spreadsheet and believe that you have solved AI. Okay, you really need to meet actual doctors. You need to understand them. Basically, you need to understand the community that's going to use your tools and your insights. And maybe a first step is to show you that medical universities exist. Okay, like this is a university, this is a big hospital, and it's something that I didn't know. Okay, when I was in your shoes, when I was an MVA student, I thought that, okay, I was in a school. You have a CS department, you have a physics department, you have literature, but I didn't realize that medicine was a thing, or that it was such an important thing. And so to demystify this, okay, we're here. The second thing is that you have 2 ways of making lectures. Okay, the first one, which is the one that is traditionally enforced in mathematics department, is to make lectures for the top 10%. Okay, that's a tradition. You go as fast as you can. You put as much technical details as you can, for 2 reasons. The first reason is that you don't want to have too many exams to correct. And the second one is that maybe you're trying actually to recruit a good PhD students, or you're trying to find good students for your field, and you don't. What? Ah, ça marche? Ok, très bien. Ah, d'accord. Ok, peut-être qu'au bout de 40 minutes, il faudra changer. Hop là. Ok. Okay, basically have this very elitist side of things. And okay, it's one way of doing things, definitely kind of works for some purposes, but when I started to talk with doctors, when I started to take lectures with doctors, and that they started to take lectures with mathematicians, I mean, some of them really do, maybe some of them are actual doctors, they told me, oh, I'm shocked. You know, why on earth do you do lectures only for the top 10, 20%? When everyone in the room is going to have a real job, is going to have real responsibilities, you know. And so I realized that people in universities, they do lectures. So some of the material is for the top 10, 20%, if top means something, but they try to convey the most important messages to everyone, because everyone in the room one day is going to have real patients in front of him or her. And basically, you want every doctor to understand the basic things, or the crucial things, the crucial messages, the crucial mistakes that you don't want them to do. Okay, and so when I understood this a few years ago, I said, okay, I think they're right. I think we're wrong. And so that's the spirit in which I designed this class. Okay. There's going to be very little technical details, because I really want to focus on geometric ideas, basically allow you to see machine learning not only as statistics or an implementation thing, but really as a geometric field. I think it's very important. That's what we're going to see. And I want to, you know, that I would like that at the end of every lecture, you keep 2 or 3 images in mind, and yet that you remember them at least for a few years. Okay, that's going to be the objective of the class. So I'm going to start the lecture with a few words about myself, a few words about the motivation, because I think that context is at least as important as actual results. But maybe I could start by asking you briefly, like, who are you? Basically, are you mostly MVA students, PhD students? Why are you here? You know, these kind of things. Okay, so maybe, you know, just one note is that last week I gave more or less the same lecture in a software developer school, which is called EPITA. Everyone was super happy to talk, etc. So please don't be so shy. So yes. Yes, exactly. For a start, like, okay, I assume that most of you are in MBA, so maybe who is a PhD student here? Okay, they're fine, great. Okay, so that's one thing. Maybe I'd like to ask you, like, who has already had a job, you know, has already worked as an engineer, maybe, or already did a PhD and coming back to school? Okay, hello, very nice. And maybe, I don't know if you have more, like, who has a mathematical major, like, you know, went to ENS or something like that and did a lot of theoretical mathematics? Okay. And I assume that the other MBA students are more like engineers. And maybe some of you are like more like software people. Okay. Hello. Okay. No, so as you see, it's not going to be hardcore mathematics, because I think it completely misses the point to do that. Okay. So, okay. So let's get started with who am I? So a short CV. So maybe I can tell you, okay, my personal trajectory is that I started doing a lot of mathematics at ENS, like 500 meters away. And then, you know, initially I thought I wanted to do logic, and then I realized, okay, you know, it's fine logic, but job prospects are not that great. And actually, I really enjoyed the class of Stéphane Mala that he was giving in undergrad at the ENS. And I thought, oh, you know, I think he's right. You know, maybe there's not a lot of proof, but it's super interesting. So I decided to go in the MVA, and then I realized that healthcare needed people like us, and that I was happy to do that. So I did my PhD in between the ENS and the UNS of Cachan with Alain Trouvé, who's giving a lecture in the second semester, you know, about shape spaces, this kind of thing. It's probably one of the most hardcore mathematics classes, but really good. Then I spent the COVID years in London doing geometric deep learning at Imperial College in the team of Michael Bernstein. And then since last year, I'm an actual researcher at INRIA. Okay, so I started to have real close ties with healthcare back in 2015. Actually, during my MVA internship, I did it doing image denoising with like wavelets. at Siemens Healthcare in Princeton. So Siemens, if you don't know, it's one of the big companies that produces MRI scans. Like you have 3-4 big constructors like General Electrics, Canon, and Siemens. And then, progressively, I started giving lecture to doctors. So here, I mean, in this very same room, we organize every year a masterclass for radiology interns in the University of Paris who would like to understand what you do, and then organizing colloquium, etc. So from a research perspective, my motivation has always been medical data analysis. Okay, as a science that allows us to go from raw physical data, that comes from sensors, and turn it into intelligible information that can be used by doctors or by the Department of Health, okay, something like that. And if you think about it, it's a field that can be cut roughly in 3 major steps. So first, you have a kind of just data reconstruction, a signal processing part where you go from the physical sensor to an image. Okay, and this very interesting field, very hard, but something that has been studied extensively since the 90s. Now you have tools that are very mature for MRI reconstruction, these kind of things. Well, you have this first step. Then you have a second step, which is how do you turn this raw image or this raw data into something a bit higher level, like go from a grid of pixels to an anatomy, a segmented anatomy, biomechanical models. So you can think of it like as a first step of signal analysis. And then you have one last step, which is mostly statistics, which is now that you have a high level representation of every one of us, how do you extract meaning, how do you aggregate actually this data into curves, something like this, something that can be used either by the doctors or by the the French Society of Radiologists. I don't know if you know about that, but in every country, you have what we call sociétés savantes, okay, that writes guidelines, that says, oh, if people have this disease and this disease, and maybe that they are waiting for a child or something, you should give them this drug. You really have those sets of guidelines, and those sets of guidelines are written according to science, and science mostly comes from this kind of statistical analysis. So in the wider context of machine learning, data analysis, I think that medical healthcare has 3 main characteristics. The first one is that we deal with highly heterogeneous data. Okay, we have to work with patient history, drug consumption history, images, medical reports. Okay, so lots of different things. The second one is that we work with small stratified samples. We have access to big data sets, like maybe all of the data from a hospital, from the APHP, or I'm going to show you, I have personally, I have access to all the reimbursement data from the carte vitale of people in France, okay, like 70 million time series. But the problem is that, okay, we are many, but there also exist many, many different diseases. And when you're interested in one specific type of disease, usually you fall back to a moderately sized data sets with maybe 1,000, 10,000 patients per group, Apart from bestseller diseases like diabetes, you quickly end up on smallish data sets. So it's not at all the same context as in, let's say, automated driving or YouTube video processing. And finally, maybe the most important point is that we're interested in sick people. So we have to deal with outliers. We have to deal with the heavy tails of our distributions. And so you cannot be satisfied with an algorithm that provides good performance on average. Okay, on average, we don't care because on average, you don't go to the hospital. So for instance, if you design a medical image analysis software, it has to be robust enough to not crash. If I don't know, someone has a nail, inserted inside the bone or something like that. Okay, so you need to be aware of robustness, which is not at all, once again, the setting that people are interested in some industries like the web processing. So this is a general context, and in actual life, I work mostly on 2 types of data. First, I work on computational anatomy, like 3D medical scans. And maybe we don't realize it when we see it with our eyes, but a medical scan is way heavier than a 2D image or even a 2D video, like the type of thing that you're going to process in computer vision, for instance, in the computer vision and object recognition class. Okay, why? Because if you want to represent a brain surface with at least moderate accuracy, you need 100,000 triangles. And a typical image that's going to come out of a modern MRI scan, you have like a 500 by 500 by 500 resolution, so it weighs 100 megabytes. Okay, so this is challenging. A second data set that I work on is public health data. And this is a context that over the last decade, okay, the size of medical data sets that are available for pharmacologists, for instance, have completely blown up. So back in the day, maybe 10 years ago, you know, all the science of drugs was done in clinical trials. You had maybe 1,000 patients in a very controlled environment. And then progressively, large cohorts started to be available for research. So first you have very important data set, which is called the UK Biobank, where you have like 500,000 people, mostly around the region of Manchester, you know, fully documented people. And now, essentially since the start of the Macron government, data from full social security data is available to researchers from specific institutions. So initially INSERM, which is like the CNRS for doctors, and since last year to INRIA. Okay, so now, I mean, the law has been written that if you're a researcher at INRIA and if you pass like a week of lessons, you have access to that. So you can start to work on this type of data, which was completely inaccessible 5 years ago. So the context is that out of nowhere, in a way, medical doctors, pharmacists, and governments, they need scalable methods. So they had tools that were working fine on 2D slices or on small clinical trials. Now they say, hey guys, I want to work on large 3D data. I want to work on the full French population. And as mathematicians, computer scientists, we have to deliver. Okay. So some specific research interests that we're going to see during the class. First, I did a lot of optimal transport for shape registration. Like, I know, maybe you're taking the lecture of Gabriel Perret. Okay, I worked a lot with him. So it's completely big part of my PhD thesis was doing this kind of thing. So here I'm showing you images of the lungs. So on the left, you have someone who is expiring. On the right, you have the same person who's inspiring. So you have those two noisy trees. So every point essentially is a point in the blood vessels in the lungs. So you have those two images. You know that there should exist a point-to-point correspondence, but obviously because it's noisy, because it's very small structures, it's not an actual point-to-point correspondence like on the discrete objects. But you know that it's there, and you try to estimate this point-to-point correspondence very quickly. Okay, because if you're able to do that, then out of nowhere you're able to estimate. You're able to see exactly how people breathe. Okay, and if you're able to see how people breathe, you're able to perform statistics on the breathing movement of people. You're able to correlate this to some diseases. Okay, and so it opens up a lot of science in pneumology. The second thing that I worked on is geometric deep learning for protein docking. So especially when I was in London. So I know how much you know about protein. I don't know much myself, but you can understand these objects as, you know, large 3D point clouds of atoms. And the thing is that, okay, those proteins have very specific structure. Actually, we know that they move, but let's assume for now that they are rigid objects. And you know that depending on the chemical properties of their surface, they are going to bind together or to bind to small elements like hemoglobin. You know, it binds to oxygen, this kind of thing. And so a big problem in chemistry is, okay, we know that this protein and this protein, those two proteins bind together. So we have data sets of this where every single point of data essentially is a biology paper, where people spent 1 year getting essentially this 3D image. And now you try to extrapolate from this kind of database and solve the problem of, given two proteins, can I say what is the likelihood of them binding together? And if they are going to bind together, how are they going to bind together? Okay. And so trying to do deep learning on protein surfaces to predict like chemical fingerprints for those binding interactions is quite interesting. And finally, something that I work on, especially this year, is doing survival analysis for pharmacovigilance. So essentially looking at all the drug consumption data in France since the last 10 years and trying to see from this data if we can detect adverse effect of drugs, like notice that some cocktails of drugs clearly lead to an increased risk of, I don't know, breast cancer, these kind of things. So it's mostly time series. So, I mean, all of this to say that, okay, I've worked in this field now for 7 years. And what's interesting is that I've seen 3 different points of view on machine learning and AI, okay, because I spent those years at the intersection of 3 communities. First, I've talked to a lot of AI experts, machine learning experts in Paris, in London, in the US. Then I talked to a lot of students like you, or at the ENS, or at the EPITA. And finally, I talked to many medical doctors, both among colleagues, in friends, family. And what's interesting is that when you try to have a discussion about AI in healthcare, you realize that there is a massive gap between what we know, what we hope, and what we fear. So if I had to summarize quickly, I say, basically, what AI experts think they know, what students like you hope, because, okay, you're here, you want to be part of the revolution or blah, blah, blah. And medical doctors, at least a few years ago, many of them, say, oh, am I going to lose my job? These kind of things. And so first thing, maybe, what do you think about this? You're here, you know that it's written like Track Santé. Once again, what motivated you to come here? I mean, you can do math, you can do many different fields, you can work in many different fields. So why on earth does all of your generation want to come doing the MVA and doing Santé? Okay. No, I mean, it's the kind of question that you have to ask yourselves. Okay. I mean, going to a class because it's trendy, it's not a good reason. Ideally, you want to go in a class which is super interesting and where you only have 5 people, because it means that you're going to have a lot of things to do. So, okay. So if you're too shy, okay, we're going to go ahead, but hopefully in the next few weeks, we're going to be able to talk about it a bit more. Okay, but personally, I think that a big problem, okay, that leads to this confusion is that we talk about artificial intelligence, and artificial intelligence deeply is a misleading term because it gives, it raises a bar of what's going to be achieved, and there is no upper limits. Whereas if you talk about statistical learning, clearly, okay, people understand that it's not going to be magic. So I think when everyone hears about artificial intelligence, even if you've been in the field for several years, you think about the kind of stuff that you read when you were a child. Okay, you think about Metropolis, you think about the Space Odyssey, you think about Terminator, maybe the Golem or something like this. And that's really the point, is that AI in all of the cultural content that we consume, that we read, AI, it's something that seduces, it's something that questions, maybe it's something that threatens you, but it never explains itself, okay? And this is why, fundamentally, now you're going to become a researcher, maybe you're going to make a thesis, maybe you're going to work in the industry, but likely you're going to do research. And you're going to see that among experts, no one ever talks about AI. It's extremely rare that people present their work and say, my AI did this, my AI did that. Okay, it's always, always, always researchers talking about models. And among experts, we always discussed underlying hypotheses. We study the properties of our models, but we try to have an understanding of what happens. And it's a bit hypocritical, I think, of the community as a whole to brand what we do as AI. But obviously, marketing is what it is. People want to hear that we are doing AI, so we tell them that we are doing AI. But okay, you should lower your expectations of what you're going to learn here. Okay, and so the aim of this class is to try to break a little bit this myth. I think if you were here, like when Nicolas Vallatisto in the rentrée of the program, he tried to convey the same message. But the aim of this class is to give you a kind of broad perspective, but most importantly, a structured perspective on what we do in machine learning. So the objectives of the class. First, it's just to present a quick overview of models that you are likely to encounter. So it's a cross-field lecture we're not going to focus only on one model, like shape spaces or these kind of things. And the thing is that when we're going to make this overview of interesting models, every time I'm going to try to highlight the underlying hypothesis and the strengths, and most importantly, the weaknesses of every method. Okay, so that you have clear picture, clear examples of, okay, in this case it's going to work, in this case it's going to fail, and it's obvious. Once you have this understanding of hopefully, it's going to give you some proper clear guidelines, about using different tools and theories, because maybe most lectures in the MVA are structured like, okay, this is the theory, you can apply it in this case, this case, this case. But in, let's say in a real life context, it's more like you have a problem and you don't know which tool you're going to use. Okay, so you need to solve the inverse problem of that. And finally, hopefully, if you're not too shy, we're going to be able to discuss really like the realities of applied machine learning, like career choices, these kind of things. I think it's important. I'm one of the youngest teachers at the MVA. Hopefully, it allows you to be a bit more chatty. Okay, so that's it for the broad overview. And today, what are we going to see? So first is that AI, okay, it's just a good model and good data, and you have a trade-off. Okay, it depends on your field. Notably, we're going to talk about the curse of dimensionality. Actually, I'm curious, like, how many of you have heard this expression already? Okay, quite a few. I know, like, was it this week? Okay, no, before. Okay. Okay, so the curse of dimensionality, and essentially that it's a combinatorial phenomenon, which is why machine learning is not just statistics. Okay, it's a distinct field. Obviously, it has lots of ties, but you need different tools. And as an example, we are going to look at the field that I'm most familiar with, so medical imaging, anatomy, and show that if you want to do good anatomy, you have at least 3 different models, 3 levels of analysis that you need to choose from. Now that then once we've understood that we always need a model, like it's never pure statistics, we're going to ask ourselves the question, how can I choose a good model? And so we're going to talk about like mostly philosophical concept about that the map is not the territory, that you can write criterions for being a good model. And we're going to see 2 examples that I really like. Okay, first, the sphere of triangles, so a bit of a mystic name. And second, maybe more deep learning related, because I think that this is what you want, some style transfer with convolutional neural networks. And then we're going to conclude about what's coming next and trying to see what happens with the computers in the other room, and maybe if you have computers. Okay. So I don't think that you have questions, but maybe you do. No. Okay, no, so okay, it was very broad. Okay, so why I say that AI is model plus data? First, you have to understand what is a data set. Okay, people always talk about data sets as being a big terabyte, blah blah blah, something like that. But no, a data set, you can always understand it as an Excel spreadsheet. Okay, Excel is the most important machine learning software ever written. Okay, so whenever you're given data set, you can think, okay, I have a big table and I have n rows. Okay, n rows because I have n subjects, and I have d columns, like d variables about those subjects. So here in this example, I assume that I have 4 people and that I know quite a lot of information, like small granularity about their diet. So I know, for instance, that this person eats quite a lot of apples, a bit of banana, but clearly she doesn't drink. Whereas this guy, this old guy, okay, doesn't like his vegetables, eats a lot of sausage and drinks a lot of beer. Okay, so you have this kind of information about people. And the typical question that you want to answer is you want to do supervised learning or just regression. Okay, it's a synonym. So you want to look for a formula, F. You want to find a good formula of those variables, so of this quantity of stuff that was eaten, of the d variables that best approximates another column, like an important quantity. So let's think heart health, okay, like the heart in good health. So that's what we want to do. It's just regression. And so the most important machine learning model, it's linear regression. Okay, you really need to understand linear regression well if you want to understand everything else. So that's what we try to do. And so the simple model of linear regression is just to assume that we can find a good estimator, a good approximation by picking a linear combination, a weighted average, a weighted sum of those quantities. And so when you do linear regression, you try to estimate weights. So here I have 6 columns, so I try to estimate 6 weights, A, B, C, D, E, F, such that A times the consumption of apples plus B times the consumption of bananas plus F times the consumption of beers gives me a number which, at least on my data set, approximates well the health of the heart that I observed. And the way you do it typically is you minimize the least squares error. Okay, that's the most vanilla statistical program ever. And you have to understand that this method, it's obviously super important. It works well in many settings, but it was designed in a low dimensional setting. Okay, the first applications of linear regression of least squares analysis, they were done by Laplace, they were done by Gauss in the early 19th century, and it was applied to astronomy. So what people knew, thanks to Kepler's law and Newton mechanics, is that the trajectory of a celestial body, if you assume that the only important object in the solar system is the sun, is an ellipse that has a few independent parameters. Like, okay, you have the length of the orbit, the eccentricity, how far away you are from the reference planes, these kind of things. But basically, you can describe at the first approximation the trajectory of every single body, of every single planet in the solar system, as you can describe it using 5 or 6 different parameters. And so the main problem that you have is to estimate the values of those parameters. And the way you do that is you stay in your room, in your observatory, and every night when there are no clouds, you get a measure. Like you observe you observe a point in the sky, and it gives you a kind of point of data for those parameters. And then you try to do it on your own, and then you ask all your friends and colleagues across Europe or across the world, and you get hundreds of data points. And so this is what linear regression was designed to do, was take a table which has 5 or 6 columns, hundreds of rows, and try to estimate good values, essentially 5 or 6 parameters. And it was used first, to estimate the trajectory of Ceres, which is essentially a big satellite, because people knew that there should be a planet somewhere between Mars and Jupiter. And so they were trying to find that. They found Ceres, and then they realized that, oh, actually, it's more like loads of big asteroids, because essentially what should be a planet has been destroyed by Jupiter, by the gravity attraction. Okay, so this is important, and this is what we know. But then the problem that we have to solve today, in 2022, is that medicine isn't 19th century astronomy. In practice, we have a lot of information about very few patients. Maybe we have 10,000 patients, but we observe so many numbers about them, like their health rate at every single time. Every image, you have lots of pixels. And so the problem of machine learning is that we deal with tables which are wider, which are more wide and tall. What makes machine learning hard is that our tables are too wide, okay? And when you have too much information about few patients, you quickly discover spurious correlations. So here in this table, just by statistical chance, on my 4 subjects, the line about the consumption of steak is perfectly correlated with the heart health. Okay, and so if I apply linear regression on this data set, I'm going to find to learn that essentially healthcare about the heart is only related to how many steaks you've eaten, and the more the better. Okay, and this problem is known as overfitting. maybe if you've done some statistics, you know about test significance and multiple tests, etc. And so I want to spend a few minutes just looking at this comic from XKCD. Okay, maybe it looks a bit, maybe you think, oh, it's too easy, it's not up to the MVA standards, but no, it's really important. So here we have someone saying, hey, jelly beans, they cause acne. And then someone saying, okay, we should look, that's exactly my job. Okay. Trying to know, okay, what gives adverse effect to people? Let's say, oh, we're playing Minecraft. No, I'm playing 3D printing, but it's more or less the same thing. And then you do a study and you realize that, okay, if you do linear regression about acne and jelly beans consumption, you do not find a very high correlation, okay? And since the correlation is very mild, maybe 0.1 or whatever, it's likely to be just explained by chance, given the distribution of your data. And so you say that, okay, the significance is about 5%. I don't know if you know what this means. I didn't know until recently because I had a hard time understanding statistics, but it means that you should just take your two samples of distribution and assume that there is no correlation, like a very simple model. And then you realize that the correlation that you observe could be explained in most cases just by pure chance. Okay, so you say we found no links between jelly beans and acne, and then you say, okay, that's fine, let's move on. And this is what people were doing 10 years ago. The problem now is that we have access to so much information that we also know the color of the jelly beans. Like, I don't know only the class of drugs that people are taking, I know precisely every type of drug. And so someone, oh, I hear it's only a certain color that causes it, and then scientists. And then what you do is you run your statistical tests against every column. Like, oh, okay, I found no link between purple jelly beans and acne. Okay, then brown jelly beans, then pink, then blue, then teal, then salmon, then red, then turquoise, then magenta, then yellow. Okay, 10 tests, no significance. Then you do it again, and then we found a link between green jelly beans and acne. Okay, basically, out of your 20 columns in your table, one of them was super highly correlated to acne. And then what you do is you publish a paper in Science and say, well, I'm a great scientist. Green jelly beans are linked to acne. And you say, yeah, if you just take those two columns in isolation, such a strong correlation could only be explained with a 5% chance of coincidence. Okay, 95% confidence, blah, blah, blah. Okay. And the thing about this is what we call the curse of dimensionality. Okay? Having access to more patients, so if you have more rows in your table, usually it's a good thing. A very rare setting in which no, you don't want to observe too many independent patients. But on the other hand, getting access to more information about each patient, so having more columns in your table, is extremely dangerous. Okay? So in the previous example, knowing the color of the candy led the scientists, so imprudent scientists, to overinterpret random fluctuation. Okay, and maybe it sounds stupid to you, but once you have a little bit of expertise in the field, you realize that the vast majority of papers published in machine learning fall in this trap. Okay, so it's extremely easy. And so my advice would be, always visualize what you do, always talk to people. And the whole lesson about machine learning classes is to give you tools to diagnose this kind of problem. In some fields, it's easy. Like in the field where I come from, medical imaging, it's easier than in most fields because we see what we do. So usually you start with the machine learning models, you say, okay, it's going to solve registration, you do it, and then you realize that, okay, maybe you get super high accuracy, but you've completely torn the tissue, like to explain a deformation, you've taken a piece there, stuck it there, so you realize it's garbage. And then you say, okay, no, okay, clearly I made a mistake, and you iterate, and then after a few iterations, you end up on a model that works and that's satisfying. But we're only able to do that because it's 3D, we have good eyes, okay? And the big issue in other fields, in general data science, is that people don't have eyes to see in dimension 10, 100. And so they stop at the first step and they do garbage. So that's a massive issue. And so a big part of what we're going to learn is, okay, how do you think about this? What are the main traps that you should avoid? Develop visualization tools, just help you not to fall in this field. Because basically, if you do that, first you're wasting a lot of time, and those are productive years of your life. You want to spend them doing something useful. And it's also obviously like a lot of money, a lot of health involved. It's really, really bad to do this. And so you can say that machine learning is about doing reliable statistics in this very dangerous setting. So high dimensional statistics. So now that we've understood that, we say, okay, one way or another, we should regularize our decision rules, put guardrails to prevent us from doing complete garbage. So a first way of doing that is to use sparsity. To say, okay, I have many columns, but I will restrict myself to decision rules that only use a handful of columns at a time. So here, maybe I can say, I only want to use one column at a time. So this is very useful, especially if you have high quality features. Okay, we're going to see that next week. So to handle tabular data in many fields like business, this kind of things, it's very good. It's a good way of regularizing what you're doing, and there exist very good software packages. Or maybe you can use those IDs to identify sources in signal processing. In some lectures, you're going to learn, given 2 or 3 microphones, to separate the different instruments in a concert, because you know that there are few instruments that have generated this sound, and so you can do source separation. Okay, so that's a good thing. But here, at least in this data set that obviously I wrote by hand, it doesn't work. Okay, because by chance or by misfortune, just one column, not a linear combination of beer and pork, but just steak, was highly correlated to the heart. So we have, for this example, we have to use something else. And so another major way of regularizing a model is to use a domain-specific structure, basically to group variables in categories that make sense for your problem, to prevent you from, to mitigate overfitting. And so a structured model is always going to leverage the geometry of the data. Here, I have grouped together apples and bananas, steak and pork, and wine and beer. Okay, and so I restrict myself to linear decision rules that have essentially constant coefficients on those 3 families. So you can say, oh, I've destroyed information. Yeah, but you have gained a lot of robustness. And then you extract a decision rule, which is interesting, and that we know it makes sense, which is that, okay, you should eat vegetables and not drink too much beer. Okay, so you can always think about this example about food groups, or in my field, like pharmacovigilance, group drugs in the ATC classification. Usually when you talk to scientists, domain experts, they already have those kind of classifications in mind that you can use as a first guess for regularizing. So a first example, which I think everyone is going to understand, is medical imaging. So first remark is that a medical image is a massive lump of data. I already told you about this. And so, this scan, it's 3D, like you have 3 space dimensions. But from a statistical perspective, it's a million dimension. It's a vector of dimension 1 million, okay? And why? Because what matters here is the fact that we have millions or billions of independent scalar values on cohorts of a few thousand patients. So maybe the rule of thumb that you have in mind is that given a set dimension, you want an exponential number of samples to get good statistical accuracy with naive methods, like histogram, binning, this kind of thing. So if you only have one number, maybe you need 5 samples to be able to learn that, okay, it's an upward trend, a curve. This is the order of magnitude that you need. So if you have 2 numbers and you want to describe a phenomenon, you need 25 samples. And here, obviously, we have thousands, millions of numbers, of independent numbers. So sampling the full space of medical images is just intractable. Another remark is that you cannot rely, at least directly, on sparsity. Okay, doing radiology, it's not about selecting those 5 pixels are the one that matters. Everything else I can throw to the bin, can throw in the bin. Okay, a good radiology exam does not rely exclusively on a handful of pixels. And so you have to rely on the other strategy, which is that you need to group pixels in 11 bundles. And so let's think together. Okay, you see this image, so it's a chest image, in case you hadn't remarked. So you have the heart, you have the lungs, you have the chest. And you ask yourself, okay, what do you see here? And what do you think that the doctor is seeing? Yes. Yes, exactly. So it's definitely one level of description which is highly relevant, which is anatomical. Like you can definitely group pixels by are they part of the same lamp. And then what's interesting is that you have a lower level of description, which is the one that we're used to when we're computer scientists, which is just to say it's a grid of pixels. So if you say, no, I have a grid, an array of numbers, maybe you're going to group one pixel, which is with just its neighbor as in a square neighborhood. So that's the lowest level. And the highest level is to say, okay, yeah, I have different organs, but on those organs, I know that some points are more important than others. For instance, on the heart, we have a lot of knowledge about the biophysics of the heart. We know, for instance, that this point, the apex, is really important. We know that the electrical influx comes from a specific point. And so maybe you'd want to describe this using a graph, of interaction between important points in the physiological body. Okay, so you can see this yourself. So first the grid of pixels, then the anatomical level, which is what you said. Okay, and just to be clear, if you only have anatomy, even if you don't understand what you're seeing, you can already do some kind of statistics. Okay, for instance, here it's a picture about the tetralogy of Fallot. So it's I think it's genetic disorder of the heart, and just observing different hearts on different patients and correlating this with the body square area, essentially how big, how large people are, you can already do things. But most interestingly, if you understand what you're seeing, if you understand that this is an image, but actually there is blood that is flowing, even if you don't see it, you know that it's there, you can simulate it, and so you can simulate the function. So, okay, I would say those are the three basic levels of understanding in medical imaging. So pixels, anatomy, and function. And as we've said, they all correspond to one way of grouping pixels, one way of defining neighborhoods. So the first one is I have this pixel in the center, it's linked to square neighborhood. The second one is, okay, this is part of the cardiac tissue, so it should be linked to its neighbor in the same tissue. And finally, okay, more a functional perspective, you link important points to each other using a priori knowledge. So that's good. And so let's go a bit into the details about this. So to think about the strengths and weaknesses of each of those three ways of describing anatomy. So the first one that you're going to learn a lot about in the MVA is just understand images as a pixel grid, okay, as an array of pixels, either 2D or 3D array of pixels. So it's a format that you are used to. It's what we call a bitmap, images and volumes. And if you go on the web, this is a type of image that you download when you use a BMP, PNG, or JPEG format. And obviously, it's a standard, for instance, in radiology, like MRI scans, they produce this kind of image. Even though at heart they measure quantum stuff, spins in an MRI scan, they are tuned to produce this type of representation of a patient. So the plus sides, like the selling points of this representation, is that first, it's extremely convenient from a computational perspective. Okay, you have a very ordered memory structure that gives you explicit neighborhood. So if you are in this pixel, your computer knows that the information about its neighbor to the right, to the left, you just have to slide on the memory on your memory device, and if you go up and down a column, you know that you can just add or subtract a fixed integer numbers, okay, to find this information. And so the fact that you have access to explicit neighborhoods without having to make any kind of complex arithmetic calculation, you don't have to compute distances. It's just like a lookup table, means that you are able to implement very fast convolutions. Okay, if you don't know what it is, we're going to see that in about 50 minutes. But so essentially local weighted averages. And the thing is that convolutions are super useful to do some tasks. First, texture analysis. So using convolutions, you're able to describe what is the texture of an image. And once you have good descriptors of the texture of an image, you're able to segment most organs. Okay, because here what separates the heart from the aorta, from the lung, from the bone, mostly it's a matter of grayscale texture.
So once you have that, it's already one task that can be solved at this low level. And second, you can do pattern detection. Like you know that a calcification in a mammography looks more or less like this. So you have this pattern, and so you can slide across the image or do something a bit more clever, but essentially slide the pattern detector and perform this type of task. So that's one thing. But then you have the second level, which is point clouds and 3D surfaces. Here, when you describe an anatomical structure as a mesh, basically you're manipulating an array with endpoints rows and 2 or 3 columns, because you have 2 or 3 spatial coordinates. And then maybe you add triangles. So on the web, it also corresponds to a standard that you know, which is a SVG format, scalable vector graphics. And this representation, you know that it's standard for video games and 3D movies. Like most assets are represented not as volumes, but as meshes that move around. Okay, so the plus side of this representation is that it's very compact. Like it's much more compact than handling around a big lump of memory. And so because it's compact, it also streams well on most computing device. Okay, because something that we're going to see at the end of the class is that you've learned complexity in terms of numbers of operations. Okay, like O of n, O of n squared. But real life complexity doesn't really work like this anymore. The main problem when you design scientific program is not how many additions or how many multiplications you perform, but how many memory transfers you perform. Like most computer programs that we write today are what we call memory bound. Okay? Basically, the computing circuits have to wait for memory to be fetched from the RAM to the compute cores. And so having a compact representation of the surface means that you have to wait a way smaller time. So that's the first thing. Second thing is that you can do high precision geometry. You know, in medical imaging, we are not interested in knowing that, okay, this is a heart, this is a nose, or this is a hand. We already know that. It's written in the metadata. What we want to do is to see that, okay, this brain has shrunk a little bit since last year. Okay, so maybe it sucks a little bit. Okay, maybe it's Alzheimer's disease, this kind of, we want to find very minute differences. And the problem with this representation was that geometric precision was completely tied to the weight of your data. Like if you want to describe something at the millimeter scale with a bitmap, you have to use super fine resolution, so super large images. Whereas with a mesh, you can, you know, it's just a matter of precision on the coordinates. And with float 32 or float 64 number, you have more than enough precision to do that. Okay, and finally, a good thing is that it's very easy to deform a mesh. Like if you want to rotate a point cloud, you learn this in middle school, you know, you apply an arithmetic operation and you're done. Whereas if you have a bitmap and you try to rotate it by 30 degrees, okay, it gets harder. Like, you know, this afternoon you have a lecture by Lionel Moisan on subpixel image processing. Essentially, the whole lecture is about that. How on earth do you rotate an image by 30 degrees? And it's very complex. Like you need a whole MVA lecture to explain to you how it's done. Whereas here, it's just middle school math. Okay, so the selling points mean that point clouds and surfaces are useful to do visualization, to do anatomy, like design an anatomical atlas, and more generally, understand shape. Like understand that some things have grown, something are shrunk. Okay, it's way easier to do it with this representation than with this one. And finally, the last level, like the expensive level, is a biomechanical or physiological model. Okay, so basically a volumetric mesh and a graph of interaction that is hard-coded by the scientists who understand what they are doing. So this kind of mechanical or biological model, usually we understand it as a finite element or as a finite element network of essentially small tetrahedron, and this is a standard format for computer-assisted design, like especially historically, just for the design of engineering pieces, for the design of submarines, of planes, this kind of thing, like Dassault system. So obviously, when you have this, it's excellent because you're able to put a lot of prior scientific knowledge in the program, in your machine learning program. So you're going to end up with something which hopefully is quite robust to noise, and that has a realistic behavior. So, which is important if you want to convince doctors that what you're doing is intelligent. So usually it's used for different things. So first, to provide physiological interpretation of the images that you're seeing. Second, to infer what cannot be seen, okay? Because typically with cardiology, what you're really interested in is the flow of the blood, and you cannot see it, okay? Some imaging devices can infer some properties of the blood flow, but what you can really see is the heart that is beating. And so you need fluid mechanics to be able to understand if the flow, if the blood is flowing, using laminar flow or turbulent flow, and depending on what's happening, you're going to decide or not to perform surgery. And so obviously you also need that if you want to simulate surgery in a convincing way. So to summarize, what we've understood is that in machine learning, you have to combine statistical regression with a relevant model. And at least in medical imaging, you have at least 3 different ways of understanding the same object. You can see it as a 2D or 3D pixel grid. You can see it as an array of coordinates or as a web of complex interactions. So typically you choose one of the 3, and ideally, if you're in a super good company, in a good team, you try to do everything at once, okay, because to get the best of all the 3 worlds. In any case, in most cases, you're going to end up defining a large structured formula, okay, that takes as input an image, that outputs an estimation of a diagnostic, something like that. And the formula F is what we call a parametric computing architecture, or that a model to fit or a network to train. But those are more or less synonymous. So now the question is, how do you choose a good model? How do you choose a good theorem? So I'm not sure I have questions. Anyway, rather to do a break. Okay, then now that you've seen that, you understand that a model is like a map. Okay, it's a warped and partial view of the world around us. So just if you take this place, okay, and you go on different websites, you're going to find many different representations of the same physical reality. First, you can look at Google, okay, the Google map plan, okay, you have 3 highlights, like you have the Eiffel Tower, you have the Sacré-Cœur, you have Notre Dame, and then you have the highways, okay? So it's a plan which is designed essentially for tourists or for people who want to drive around. Then you have the RATP plan that essentially completely distorts the geometry, the 2D geometry of the city, but that highlights the network transit system. It rectifies trajectories so that they are easier to see, etc. Third map, exactly of the same location, just Météo France, so a big zoom out. And we don't care at all about roads. We only care about pressure fields, winds, etc. So already 3 different things. 3 totally different representation of the same object. And obviously, you know that if you want to be a good data scientist, if you want to be a good geographer, you have to pick the map which is suited to your targets. And it would be a bit stupid to always pick Google Map or always pick the map of Météo France. Maybe, I think a setting in which you've already been warned about bad projection distortions is just maps of the world. Okay, you know that back in the days, people thought that the world looked like this. Okay, very simple representation. And then, I don't know, maybe it was like in the 16th century, you have Mercator, who came up with this map. Okay, and this map, actually, it's very useful if you're doing navigation, because the main property of the Mercator map is that the trajectories that cut meridians at a fixed angles are straight lines. And so, if you're in your small boat in the middle of the Atlantic Ocean, what can you do? Well, you say that at noon, you know that, okay, the sun is here, and you can compute the angle between the sun at noon and your trajectory. And you can say, okay, I want to stick to this cape. And you stick to 30 degrees. If you say, okay, I'm 25, I turn right, turn left. Okay, but this is what people were actually doing. And doing this simple navigation process essentially drives you in a straight line on a Mercator map. So this is why it was designed. And then people started to use it for everything else. Like, this is how we teach geography to children, etc. And obviously, I'm sure that you know that this is a terrible idea, because if you look at this, you believe that Europe has more or less the same size as Africa, which is obviously totally false. Okay, Africa is way larger than Europe, the US, and China combined. Okay. And so this is why some society now, they tell you that you should use Winkle. So, you know, I hope that this is striking enough to tell you that you see that this happens in 2D on something that everyone knows about. So imagine what can happen in machine learning. Okay, all those models, they come with strong biases, or maybe they just reflect what people believe is important. You know, you have some maps of the world of the Middle Ages that look like a circle, cut in the middle, cut in two halves, and then a third quarter. So you had just a circle cut in three pieces, and in the center you had Jerusalem. And that's because this is what mattered to people back in the day, you know, to understand the world in a kind of spiritual sense. Jerusalem in the center, and then those three pieces, I think they corresponded to like the three sons of Noah, this kind of, you know, and it made sense for them. And now that you're going to have real job, you're going to do real stuff, you should know what are the implicit priors that are behind your feature set, behind your representations. Otherwise, you're going to have lots of biases. So this whole concept, okay, people thought about it a lot back in the 30s, 40s, and they come up with a single motto: the map is not the territory. Okay, the map is not the territory it represents, but if correct, it has a similar structure to the territory, which accounts for its usefulness. Okay, so here the important words are structure and usefulness. Okay, a map should be useful, otherwise it just stays it just goes to the bin. So a quote that I discovered when I was doing a PhD by Georges-Louis Borges in 1946 really struck with me. So I would like to read it with you. Okay, it's called On Exactitude in Science, and it's just a paragraph long novel. Okay, so it's exactly this text, but in Spanish. And what's written here? So, okay. In that empire, the art of cartography attained such perfection that the map of a single province occupied the entirety of a city, and the map of the empire, the entirety of a province. In time, those unconscionable maps no longer satisfied, and the Cartographers Guild struck a map of the empire whose size was that of the empire, and which coincided point for point with it. The following generations were not so fond of the study of cartography as their forebears had been, so that the vast map was useless. And not without some pitilessness was it that they delivered it up to the inclemencies of suns and winters. In the deserts of the West, still today, there are tattered ruins of that map, inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. Okay, and it's an apocryphal citation, supposedly from the 17th century. Okay, maybe you see that. I'm saying, oh, it's not what the MVA is about. I want people to study map and all that. But no, I can tell you, you know, when I okay, no, so that's fine. So anyway, it's maybe a good time to make once again a short break. It's something. Maybe when you're a student, you say, okay, good, but when you started to do science, you realize how true everything of this is. Like it's personally, I'm very impressed that this guy, who is not a scientist by trade, was able to capture what is happening in our communities so well. Okay, because what do you have here? Maybe if you don't understand the metaphor, okay, what you have here is you have a scientific field, let's say cartography, that started by doing useful things like small maps. People were able to go around, etc. And then this community started to have higher and higher standards every year. And they started to become obsessed with perfection. They stopped talking to the clients. They stopped talking to the general society. They just stayed within themselves. And they took their pride in the accuracy of the maps. And then, you know, they started to essentially design models that were more and more accurate, but also more and more cumbersome, and at the end quite useless, because they hadn't simplified anything. They had just taken a photo. They had just described what already exists and what everyone can see. So that's the first step. The second step is that people think the next generation of students, basically the people who are not already invested in this field, see that this is useless. And then instead of going back to the good maps that were produced 20 years ago, they discount everything and they forget everything. And unfortunately, this kind of dynamic is exactly what is happening right now in several scientific fields. So maybe it's recorded, maybe it's not politically correct. But when I was doing my PhD, I was very struck by the discussion I had with the people who do numerical analysis, like fluid mechanics computations or in-field games. Basically, those kind of fields 10 years ago, they had all the hype. Okay, basically, you would have wanted either to go in the mathematical finance programs or in those programs. I have many friends who went in those fields, but then the problem when you read on this literature, which is about doing fluid mechanics, simulating fluid mechanics, is that this literature has become so complex that even someone like me, or basically someone with a good engineering degree, comes from a good school, is completely unable to understand what on earth is happening. Even between themselves, they still have no clear rules about, okay, for this equation, you should use this and that. And on top of that, they had a community dynamics where different labs, different teams didn't want to share. And so until very recently, you wanted to Google, I want an Navier-Stokes solver. You think, okay, this field has been funded since the 1980s. Of course, there should be a Navier-Stokes solver, a simple one, just for me to simulate a basic a glass of water. It doesn't exist. And because of that, essentially, they got a bit superseded by AI in a sense, or they had to change, and they stopped being able to attract students. So essentially now you're here instead of being in the Department of Mathematics of Polytechnic to learn about it. And it's a massive shame because now all of this knowledge, personally, I love reading textbooks about hyperelastic materials, simulation. I think it's super interesting. That's why I showed you a simulation of the heart. I think it's great. But everyone forgets about it. And it's very likely that in 20 years, no one will be able to reproduce these great things. So obviously, this was very pessimistic. The new generation, they understand that their field has a problem. And so now you start to have open source implementations that are good and accessible by outsiders. But it's a real dynamic. And so maybe some of you are PhD students already. Some of you will do a PhD. And I'm really warning you, okay, don't fall into this trap, okay? Because the trap is to take what your PhD advisor did and add another layer. But then you have to realize that what your PhD advisor did was simple, it made sense, it solved the problem, and people liked it, whereas an incremental improvement, likely, it's just going to interest your small community. And so it's going, if you do that after 2 or 3 generations, it starts to be a bit of a waste of time, okay? So, choosing the correct problem is more important than technical accuracy. Okay, and technical proficiency is obviously important. So it's important that you work well, etc. But kind of the wisdom of when should I stop, what problem should I solve, is the most important quality. Okay, as a scientist.
What we've seen, and I hope that the metaphor is stuck with you, is that is model a machine learning model is just a map. Very high dimensional speed, very dangerous. Okay, and what we know from our day-to-day experience is that a good map should have at least 4 good properties if it pretends to be useful. First, it should highlight the key points and rows that are relevant for the person who are going to use it. Okay, so this is very much a task-specific objective. Like you're not going to write the same map for cars as you would write for bikes or for archaeologists. Okay, and this is why in the MVA, you have a class for medical imaging, natural language processing, computer vision. Those are different categories. Okay, and dreaming that you're going to come up with a single model that's going to solve everything, it's just completely not realistic. Just like you don't have a single scientist to solve all the problems available in science. Okay. Second, you want to hide everything else. You want to hide unnecessary information to reduce clutter. And for this, really, the lighter the better. And maybe this is not something that's going to be obvious for you as a PhD student, but it's going to matter a lot for our customers and other scientists. Okay, no money needs to be involved. So heavy maps will be discarded by the next generation. Right now, when I'm giving you a lecture, I'm highlighting the simple, nice ideas from 10, 20 years ago, and we are completely forgetting everything else. Okay, so if you want your work to stand the test of time, maybe try to tell yourself, is it going to be included in a textbook 20 years down the road? And otherwise, maybe do something else. Third, you want to be accurate, obviously, but only up to a required tolerance. Okay, and there is a trade-off here between simplicity and accuracy. And think of the metro map. It's not at all accurate in terms of XY coordinates on the real sphere, but it's very easy to read. Okay, and it's much more useful this way. And finally, you want to try to be transparent about emissions and distortions. Okay, just like this Mercator map versus the better one. And this, okay, is the main trap that we always forget and that we should not forget. You know, I think as machine learning scientists, you're going to know that you have to highlight important stuff, hide everything else, be accurate, maybe too accurate. But very likely, just like me, you're going to forget about the bias and all the distortions that you're including. Maybe to you, they're obvious. Most of the time, you don't know either because it takes time and you don't have time for this. But clearly, the people who are going to use your tools, they will not know about all those hidden biases, and it's a recipe for disaster. Okay. So all these points, obviously, they apply to machine learning models. So you want to highlight the stuff that matters, discard the rest, be accurate, be transparent and honest. And so, of course, okay, the raw performance results do matter. Okay, accuracy, it's a real thing. You want to design models that do not output garbage. But, you know, quantitative performance is very overrated, especially in academia. Like in academia, people, they like to publish papers where at the end, you know, they have a model, then they have a table, they say, oh, look, I'm 5% better, 5%, usually it's good, maybe I'm 0.5% better. They get accepted, they're happy. It's, you know, it's not really good science to do that. I think you can see it as an outsider, so don't fall into this trap. Once you do, you have to realize that qualitative progress is much more important than quantitative progress in the real world and for scientists. It's much more important to be able to solve a new problem or to solve a problem in a different way or to solve problem with fewer dependencies, with more noisy data. You know, enabling people to do new things is much more important than enabling them to do them a little bit better. You know, and in this setting, going 10 times faster or making 10 times fewer errors. Okay, this is super important because it enables a whole new range of applications. But making the same thing just 10% faster or 10% more accurate, but you know, going from 10 errors to 9 errors at the cost of increased model complexity, maybe you're going to get published, but no one is really going to care. Okay, and so you want to avoid that. So most importantly, a good model, it should be legible, like people should be able to understand that. And personally, I think that the main criterion for a good model is that it should enable creativity. Basically, it should be just like a map. It should allow people to do new things. And so, you know, so far we've seen lots of abstract concepts and all that. I want to be concrete, and so I'm going to present to you two models that I really like. Okay, so first, my favorite theorem, which is a sphere of triangles. So, okay, true surprising thing, and more surprising even, that the story of the sphere of triangles starts with menhirs. You know, those megaliths that were erected back in the prehistory. And more precisely, with the distribution of megaliths in the Land's Peninsula. So here it's a map. You have London, you have Normandy, you have Wales, and then you have Cornwall. And this, it's a peninsula like 15 kilometers by 15 kilometers, which is called Land's End. And it's basically the English Finistère. And as you can imagine, if you're English in prehistory, you believe that this is the end of the world. Okay, you've never been elsewhere. So it's a very significant place. And you have lots of menhirs in this place. So this is a map, and essentially every number corresponds to a menhir. So you have 52 menhirs in this small peninsula. Like, it's not too small. Like, the menhirs, they cannot really see each other. or at least this manier cannot see this one, but okay, they're here. And then a question that people ask themselves 100 years ago is, can I see alignments here? Like you see this map and you say, okay, like here it looks like a line, here it looks like a line, but it's not clear. You know, like in Stonehenge, it's very obvious that there is structure and people know that, okay, it's clearly a solstice calendar, like there is very obvious astronomical purpose. But then for those type of point distribution, it's not so clear. And the thing is that in the 1920s, 1930s, 1940s, some people claimed that there were alignments, that they existed, even on sites where the different maniers couldn't see each other. You even have people who wrote books about manier locations, like one in Galicia, one in Brittany, one around Bordeaux, you know, and they say, oh, there is a line here and there is meaning, okay? And obviously, because there was no GPS back in the day, people believed that people in the prehistory, they were either able to sense some kind of earth energies, or maybe they were guided by aliens, you know, like, so, and it was a legitimate question back in the days, at least for like neo-pagans. They wondered, like, is this real or is this a hallucination? And archaeologists try to answer this question. And so you have an archaeologist, I think like Simon Broadbent, he talked to his friend David Kendall in Cambridge. He explained to him the problem. And this motivated David Kendall to ask himself a question. Okay, assuming that I drew 52 points at random in a square, how many flat triangles, like if I consider all the three among 52 triangles, how many of them are going to be flat? Like, and by flat, I mean 180 degree or 179, you know, you lost some room for, okay. And this is a statistical question on triangles. And this prompted a remarkable series of papers, like in the 70s, 80s, like the diffusion of shape, so both statistical things like alignment in two-dimensional random sets of points, or archaeology papers like simulating the ley hunter. The lines are called ley lines, and so people were looking for lines. And actually, this is really the birth of modern shape analysis. So I'm going to show you how should you think about this problem, or a good way of thinking about this problem. First, we understand that we're only interested in the angles of the triangles. So we want to work with triangles up to similarities. And by similarity, I mean a rescaling, I mean a shift, translation, and a rotation. So if you think about it, a triangle, a planar triangle, it's given by 3 points in the plane. So you have 6 degrees of freedom, x, y times 3. So you have 6 parameters. And when you say that you want to work up to similarities, you are killing 4 degrees of freedom. Because first you are killing the scale, so from 6 to 5. Then you are killing the position, which is 2 degrees of freedom, so 5 to 3. And then you want to kill the rotation, which is yet again another degree of freedom. So you end up with 2 degrees of freedom. So you can see that, okay, triangles up to similarities, you should be able to describe it in a 2-dimensional space, okay? So actually, there is a way of doing it, which is to say, okay, I assume that my triangle is not completely degenerate. So for a start, let's assume that A is not equal to B. Then you have a triangle like this. You know that using a translation, rotation, scaling, you are able to send A to the point -1, 0, and B to the point +1, 0. And just you do it a simple formula. And then obviously you only have a single free degree of freedom, which is the position of the vertex C. And so here in this model, maybe you can think that the situation where A is equal to B corresponds to the situation where C is super far away. Because if C is super far away, with respect to C, A and B look similar, so at infinity. And the model doesn't take into account what happens when A is equal to B is equal to C. Okay, so it's kind of the degenerate point in this model. But so you have this, and so you say, okay, a shape of a triangle can be identified with a point in the plane. And so maybe what I can do is I can take a plane, and at every location, I'm going to draw the triangle that corresponds to it. Okay, and this is what's presented here. Okay, so we're going to make a break after this session on triangle so that you can draw it on your sketch. I even printed a small 3D model that you can look afterwards. So you can see that everything is real. But you have this plane of triangles, and then you say, okay, so I have solved my question. The set of triangles is a plane. But then you ask yourself, okay, now that I have this embedding, this representation of a set of triangles, can I draw interesting sets? And maybe the most interesting set are like the set of flat triangles. So flat triangles, they correspond to a situation where C is on the same line as A and B. And so in this diagram, they correspond to all flat triangle shapes are on the horizontal axis. Okay, and here you have the equilateral triangle with positive orientation, here negative orientation. And then you say another interesting set is a set of isosceles triangle. So you look at the triangles which are isosceles with respect to C. So with respect to C, is going to be all the triangles basically that correspond to points on this blue axis, on the vertical axis. So that's it. So here, so far, okay, so good Cartesian. And then the miracle happens when you say, where are the triangles that are isosceles with respect to A? And then if you draw the set of triangles which are isosceles with respect to A, you end up with this shape, kind of circle or ellipse. And then if you draw the set of triangles that are isosceles with respect to B, you end up with this shape. And then when you see that, you say, oh, it reminds me of something, and this is where mathematical culture is important. It really reminds me of the projection of a sphere onto the plane. It looks like a weird, distorted map, a bit like the ONU, the United Nations organization, like the symbol. It looks a bit like that, where here you have the North Pole, here you have France, here you have Antarctica, here you have the US, here you have China. Okay? And so when Kendall drew this picture for the first time, it was a bit mind blown, and he realized, okay, maybe I should be able to design a mathematical formula that takes as input a triangle and sends it to a point on a sphere. And so that's what he did. And you end up with this shape. So this is what the space of triangle looks like. So I've forgotten if it's really a stereographic projection or if it's a little bit more complex than that. But you just do that. So you take your triangle shape, you put it on the plane, and then you map the plane on a sphere so that this becomes the North Pole, this becomes the South Pole, and most importantly, so that the sets of isosceles triangle become meridians at 0, 60, 120 degrees. So you can look at that. Okay, so here you have the equilateral triangle, isosceles triangle, flat triangles. It makes sense, and you can look at it from every direction. Okay, so you can look at it here. It makes sense. Like it's a very smooth parametrization of the space of triangles. And this space, first, it has lots of nice properties. First, this representation, it respects the main symmetries of the set of triangles. Okay, as we've seen, the sets of isosceles triangles with respect to A, B, and C correspond to 3 great circles that are equally spaced with each other. So it's much more elegant. You have highlighted much more interesting structure than what we are doing with this first embedding. Okay, the second embedding has captured something more interesting. Second is that when you take a triangle and you flip it, basically on the sphere, it corresponds to taking the same point, but in the southern hemisphere. Or if you were in the southern hemisphere, going up in the north. And finally, if you come back to this shape, when you take the equator of flat triangles and you take those 60, basically you had the tangerine and you've cut it in 12 pieces. 12 pieces where you have all the kind of real individual triangle shapes. And this number 12 actually corresponds to the set of transformation on a triangle that preserve its shape. You have 6 permutations of the vertices A, B, and C times do you take the triangle or do you take an axial symmetry? So it's kind of elegant. So this is just from a topological perspective. You see that this representation has a right topology to describe the set of triangles, but there is more. Okay, and this is why it's an exceptional model. First, this map has good geometric properties of the spherical embedding. So let's call the embedding K. So K, it's a function that takes as input a triangle, so R times 6, but without considering the state of A equal B equal C. Okay, this is out of the model. And it sends it onto a sphere of diameter 1. So this is just the map that I used. So I implemented it to produce the slides. In practice, it has an okay-ish expression, using trigonometric formulas. And then it's interesting because you say, okay, I have two triangles, A, B, C, D, E, F, and you say, what is the distance between them up to similarities? And one way of doing that is to say, okay, if I have two triangles, not up to similarities, the basic distance between them is a squared Euclidean distance between the vertices. So you take the distance between A and E, between A and D, B and E, C and F, you square it, it gives you a distance. And then the distance up to similarities could be the minimum of this quantity, but when you allow the first triangle to move around in the space with a similarity. So it's what we would call a quotient distance between the two triangles. So you say I have ABC and I consider the minimum over similarities. So 4 degrees of freedom of S of A minus D plus S of B minus E plus S of C minus C. And then, miracle, you're going to end up with a formula that only depends on two things. First, it's going to depend on the scale of the target triangle, and this is normal because, like, if the target triangle doesn't move, like, you can do what you want with the similarities, but the distance between the vertices is going to be scaled by the scale of the target triangle. But then the remainder only depends on the shapes of A, B, C, D, E, F, and this is exactly equal to the core distance between the two shapes in R3. Okay, and so you've seen that the core distance on the sphere of Kendall corresponds to the Euclidean distance on triplets of points in the plane up to similarities. So second good argument, we said, okay, we've really understood something. Actually, this is a way, taking this formula is a way of finding the correct formula for K. Like, saying. And then you have a third property, which is the one that interested Kendall initially, which is what about statistics? And so you say, what does it mean to take a random triangle shape? So maybe you can say, okay, a random triangle is I take ABC independently following some kind of law, and then I look at the shape of the triangle. But then you have the question, how do I pick ABC? Like, what is the law on the plane that I'm going to use for the points? And then you say, okay, maybe I should pick a circle, maybe I should pick a square. It's not, you don't want to induce too much choice. And so maybe if you've done math and statistics, you're going to say, okay, the simplest distribution that I could draw points from is a Gaussian distribution, isotropic Gaussian. So you do that. You say, I draw ABC, IID thanks to an isotropic Gaussian distribution. And what do you see? If you do that with 10,000 triangles and then you plot an histogram on the sphere, you realize that you have a uniform distribution. So the most simple, obviously, as far as mathematics are concerned, the most simple way of generating triangles gives you the uniform distribution on the sphere of triangles. And more interestingly, you say, okay, but I want to complexify the model a little bit. What is the simplest way of complexifying a Gaussian? Maybe it's to prevent it from being isotropic and say, okay, there is a direction where there is more variance. So maybe you can do that. You increase the variance along the x-axis. Then you end up with something which is not uniform anymore, but surprisingly, it's only going to, the distribution on the space of triangles is only going to depend upon the altitude across on the sphere. So clearly we have captured something interesting. And so when you have super high variance in one direction and low variance in the other, you generate more flat triangles. So your distribution is concentrated around the equator, which is the equator of flat triangles. Okay, so what we've seen, summary. Kendall, back in the 70s, showed that the space of triangles, it's best understood as a sphere. for 3 good reasons: topological, geometric, and statistical. So that's really a remarkable result. And once you've seen it, you cannot unsee it, at least the topology one, like this. Maybe the geometry, you forget about it, but understanding that this is a continuous way of parameterizing the space of triangle shapes, you're probably going to remember this. Most importantly, from a historical perspective, his theorem showed that shapes, and by shapes, obviously, I'm going to mean organ shapes, brains, hearts, you see them more elegantly, like they belong more naturally to a curved geometric space. You understand more things about them if instead of seeing them in a plane where remarkable sets have strange ellipsoidal shapes, you say, no, my shapes, they live in a curved space, and in this curved space, natural things are straight lines. Okay, and this is how this idea, this core idea that shapes live in a curved space, is at the heart of modern software in shape analysis. So here I'm showing to you pictures that come from a paper, 15 years ago. They're already able to implement things well on 3D shapes, where, okay, what people do in this paper, they say, I'm going to define a geometry, they say a Riemannian metric, on a space of elephant shapes. And the way they define this metric, so we're going to see that in like a month, quickly, is they say, okay, they assume that they have a nice gummy material. And once you have this kind of physical model in mind, you're able to derivate nice equations for the local geometry. So they say, I have my local geometry that is induced by a super simple mechanical model. And so it allows me to compute curvature, and most importantly, to compute straight lines between 2 different shapes, to compute geodesics. And so what they do, they say, okay, this is my shape A, this is my shape B, and now I want to compute a straight line, and I want to extrapolate a little bit. And this is what is displayed here. So this is a geodesic that interpolates and then extrapolates between those 2 shapes. And so it's a straight line in a curved set of shapes. Here, the same thing, but with hands, simple hands, where, okay, in blue, I hope you can see the colors. This essentially, so this, and you interpolate nicely, and then you extrapolate. And here you see, it's important because if you had just handled this data as vectors, using a flat geometry, you just had the x, y, z coordinates, and then you had used flat linear equations, then your geodesic would have basically used straight lines for the displacement of every single point. You would never have been able to capture this kind of pseudo-rigid transformation. Okay, and this is where the idea of curvature comes in. Okay, maybe another thing that I really like is that once you have a good metric, a good geometry in the space of shapes, so here shapes of hand, you're able to solve least squares interpolation problem. And so you're able in real time to interpolate between different shapes of hands. Okay, and so these kind of things, so it's studied heavily, I think, in 3 different fields. So first, it's studied in computer vision, okay, where people want to understand the shapes of people doing gymnastics or just walking in the streets, understand what is happening. Second field is obviously medical imaging, okay, where we are super interested in the shape of organs. And the third field is computer graphics, which, if you're not aware, it's a super nice scientific field. Basically, it's a conference in which you have Pixar, Adobe, explaining, okay, how they simulated the snow in Frozen. It's a very, very nice paper where they explain how they did this. And so these people, they say, basically, my artists, they drew an animated puppet skeleton. Then they have the storyboard where they have this shape, this shape, this shape, and then I want to smoothly interpolate between them, because first it's cheaper to store. Instead of storing 24 frames per second, you just store 1 frame per second, and it's also much lighter in the design process. Okay, so that's I would say a first example of a really cute geometric ideas that has very real applications. And for me, what really mattered, in terms of mathematics, is that Kendall didn't stop here. He understood that there was more structure to be investigated, and so he made the effort to switch to this spherical curve perspective. Okay, so we're not going to spend more time on this. There's a full lecture on the subject in the second semester, but just to give you a taste of it. Okay, so we've seen, if I recap what we've told so far, okay, so AI is just about having models that you train on data. You want to pick a good model, and so I gave you abstract guidelines. And notably, I told you that what matters for a model is that it allows you to be creative. It allows people to do new things. Okay, doing new things is more important than doing all things a little bit better. Okay, and so I want to highlight in this introductory lesson that this concept, you can apply them to everything we do. Okay, from very simple middle school-like mathematics, so that's what we saw, until very advanced AI applications. Okay, and so this is going to be my second example. I think one of the most iconic applications of deep learning, convolutional neural networks, which is art generation or style transfer. So first, I'd like to know, like, for new MVA students 2022, what do you know about convolutional neural networks? Like, have you already implemented one? Never? You don't know what is a convolution? I know, because I did an MBA back in 2015. No one knew about that. We had done a little bit of MATLAB before coming, and that was it. Okay, and we learned everything on the go. I don't know today what's the situation.
Well, basically, you have, when we use them, so I'm not minds, so very more engineer oriented. So I use them, but I never implemented one. I know some of the basics. I know what convolution is, but implementing.
Okay, so maybe if you could raise your hand first, if you know what's a convolution. Okay, so nearly everyone. Okay, which is impressive. Second, maybe if you can raise a hand if you're taking a lecture on deep learning. Okay, so not everyone, which is very interesting. Okay, because it's very good that you do diverse things. Not everyone in the same class. Okay, and maybe if you've already used NumPy, and no, but I mean, my generation, no, and PyTorch. Okay. No, you see, I mean, the curriculum definitely evolves. Okay, so that's interesting. Thank you. So, okay, remember that picture? We said, okay, we're going to do medical image analysis, and you have 3 levels of description: pixels, anatomy, function. And underlying, the underlying message about the whole class is that, especially in imaging sciences, essentially this level of description is very mature, and we are still working on making the level 2 mature enough to be deployed in the industry, and level 3, it's still very active research. Okay, so that's a bit how things are moving, but obviously, I think for a start, you should start with simple things. And so let's look at what we can do when we see images as big arrays of pixels. So the first way of grouping a pixels with their neighbors in a square window. So just in case you've forgotten, okay, convolution product is just what we call filtering. Okay, it's what you have in Paint when you say I want to apply a Gaussian blur. So convolution, it's a weighted average of the neighboring pixels, and you can understand it as a cheap generalization of the product, A times X, the kind of thing that you would use in a linear regression, but where you, instead of using a scalar parameter A, you use a small filter phi. Okay, and so here you have phi, a small image whose coefficients tell you that, okay, the center only cares about himself. Okay, so Dirac convolve with himself, just gives you the same image. But if you are more interested in others, if you say, no, I also care, I want to take a weighted average with my neighbors, then it corresponds to using a filter which is a bit larger with positive coefficients, and you know that it corresponds to a blurring. Okay, so if convolution was only used with positive coefficients, it wouldn't be very interesting, just cascades of Gaussian blurs. But what people understood back in the 60s, 70s, okay, this is very old stuff, convolutions were not invented in 2013, where people understood that things get interesting. when you authorize negative coefficients. Okay, so for instance, you say, okay, now my convolution filter has negative value and positive value left, right. So now this operation measures contrasts along the x-axis. And when you apply this, you retrieve something that looks like an edge detector, at least a detector of vertical edges, because in regions that are flat, like very white, very gray, very black, you get 0. But when you climb up a hill, you see signal. And if you don't care about going up or going down, you just say, I want to detect edges. You apply what we call a nonlinearity. So maybe just absolute value. Okay. Now people use like the ReLU, which is a positive part. But, it's an arbitrary choice. So that's it. And okay, it's very interesting to see that such a simple operation, just minus plus on an array with a fixed memory structure, already allows you to express something that has meaning. Okay, and this is why the convolution is so interesting. So now you say, okay, I take a different filter, maybe vertical, you detect horizontal edges, diagonal, okay. And so this is something that was studied a lot, especially since, in the 60s, people studied the brains of cats. So they took cats, they did surgery so that they had a glass window on their visual cortex so they could observe what happened in the very first layers of the cortex of mammals, of the visual cortex. And they saw that, okay, something that looks like a convolution is happening, like very local. And so this was studied under the name of Laplacian pyramids in the 70s, 80s. And then, in France, between 1990 and 2010, people called this doing wavelets. Okay, wavelet was a big thing. So you had very well-known people like Yves Meyer, Stéphane Malat, which gives you a lecture, Ingrid Daubéchy, and especially all these people were studying algorithms on images that shared the same structure. They started with a full image and they applied convolutions with a bank of filters that was deemed interesting. Okay, and so you obtain information at the microscopic level, at the pixel level. And then you say, I'm also interested in the same thing, but at a higher level, because you have this prior that, for instance, if you want to detect a human body, basically, what is a human body? It's a trunk, arms, legs, face. And a face, it's nose, eyes, mouth, ears. And what's an eye? It's edges like this. So because people knew that we had this, we thought that human vision works a little bit like that in a multi-scale fashion. They wanted to have multi-scale algorithms. Okay, and this is what they did. And so the way you do that is just that you apply high-pass filters like edge detectors at a given resolution, and also apply a low-pass filter, subsample it. So it's what we call mean pooling. So you take local mean, but at a smaller resolution, and you iterate the same thing. And so it allows you, this method allows you to turn your image into a collection of images at different resolutions that were called like wavelet coefficients. And the intuition behind that is that the image is turned into a collection of relevant coefficients, just like a WAV audio, like a raw audio file, could be turned into a music score. And you want to work on the music score. Like you want to have, I don't know how you say it in English, croche, noir, and whites, okay, like different rhythms, different legs. But obviously, if you want to do music analysis, it's much more convenient. Okay, so then, obviously, the question was, how do you pick the convolution filters? And back in the day, we didn't have computers that were powerful enough to train them on very large data sets. So people were already trying to do it, but on small data sets, it wasn't that great. And so instead, what people think, like people like Ingrid Daubéchy, they said, okay, maybe what matters in my representation is that it should be as sparse as possible. A good representation is a compact one. A good model is a small one. And so a criterion is, if I give here a natural image, how good is the compression ratio? Okay, like how many non-zero coefficients do I have? And you want to have the fewest coefficients. And so the super nice theorems that were developed 20 years ago were to say that, okay, if my image is a cartoon. So a cartoon, what's a cartoon? It's a picture that's where you have lines, like you have different pieces. The frontiers between the different pieces are piecewise polynomials. And inside those different pieces, you have constant values or linear gradients, or maybe quadratic gradients, but something like a cartoon. And what people show that if you have this polynomial prior on natural images, then you're able to design optimal filters. Okay, and this is what the wavelet, this is where the standard wavelet coefficients come from. They are the filters that are optimal if you assume that you're only dealing with piecewise polynomial images. And this theory allows people to find good small filters. Obviously, they don't work perfectly because in real life, no image is a real piecewise polynomial thing, but it kind of already works. And so people were able to design very, very efficient compression formats like JPEG 2K, JPEG 2K, so JPEG 2000 format, okay, which is not the standard on the web because JPEG, which relies on Fourier coefficients, was already there. Okay, so there was no need to change it, but it was the most effective format, compression format, when we started, to watch digital movies. I don't know if it was the same time as Avatar, 3D movies, but essentially when we switched from celluloids to numerical things. And so now JPEG 2K is a standard format in the movie industry. So when you go in the movie theater, what you see is a collection of images that are encoded as JPEG 2K images, so essentially using this kind of hierarchical representation. So that's standard things. That's what we learn, or what the people a little bit older than I am learned when they were in the MBA. Okay. What?
You said images are considered piecewise polynomial. Do you mean like some straight lines in the image or some contours? Or?
No, so more like imagine an SVG icon. So you have so essentially it's splines. So you assume that you can draw everything using splines. And if you have that, you do that like Gabriel Perret. You type Gabriel Perret PhD thesis, it's about this kind of thing. Okay. So that's good, but now you know that it's 2022. And so you do not have to worry too much about this anymore because our computers are so good that we can just train, basically treat the problem of finding good wavelet coefficients as a regression problem. And so you train them on ImageNet. So we take networks, algorithmic structures that have the same shape as before, as always. So you have your image, you apply convolutions, maybe you downsample, and then you reapply convolutions, you downsample, and essentially what now the criterion is not so much compression as it is separability of interesting classes. And so that's why we train most convolutional neural networks on classification tasks. Essentially what we ask from our CNN transform is that if I input, let's say, digits, and then at the end on my final representation, a very simple statistical program like a multi-layer perceptron or logistic regression is going to be able to disambiguate the class of the image. So different prior, but same architecture, let's say, as what we use for compression. And so that's why you can understand convolutional neural networks as a data-driven codec for your data. You think that JPEG 2K, it relies on a model for natural images that is computationally cheap. So we've seen that convolution are super cheap to compute on grid images. It's translation equivariant, like you translate your image, translate your JPEG encoding, and it encodes this multi-scale prior on natural images that we think is important. And so now what we do when we do CNN is that we tune the parameters of this kind of parametric architectures on a labeled database, and you get a network. And what I want to stress in this slide is that you have lots of people who tell you, yeah, convolutional neural network, it's a black box. I spent 2 days on 8 GPUs. I trained it on a neural network, and then the only thing that matters is the performance score. And many people in deep learning, especially many students, many PhD students, this is what they do all day long. They train bigger and bigger neural networks, and a bit at random, they add new blocks and they hope that it's going to work. Okay, it's one way of doing things, but it's not very productive. And for having been in a lab like this, for having met people who do that, it's not very enjoyable. Like to see your work as just, I design a bigger network, I don't understand what's happening, I wait for 2 days, I get a performance score. I think good ideas come when you try to understand what is happening. when you try to inspect what is in your model. So that's why in the next few classes, we are going to have lots of images, lots of visualization tools. You can understand them as diagnostic tools. Those big neural networks that you're going to train, they have sometimes billions of parameters, and it's a shame to compress everything as just one single performance score, which is noisy because it's a stochastic optimization. So it's very cumbersome. And so on standard vanilla CNN like ResNets, you can really understand it. I think a productive way of seeing your convolutional neural networks is to understand it as JPEG 2020. You have your image X, and you say that, okay, I apply my convolutional layers and I get activation maps. Basically, I look at the result of my convolutions at different scales, and you can think of it as descriptors at a microscopic scale, at a mesoscopic scale, at a macroscopic scale. And so this way of working is productive. And why I say that is because this is exactly how people thought about their convolutional neural networks, when they designed this iconic application, which is deep art. So what is deep art is you take a painting, you take a picture of your cat, and you say, I'd like to have a painting of my cat, but I don't want to pay a painter. So what you can do is you say, okay, I apply my JPEG 2K, my JPEG 2020, and so I get descriptors at a microscopic, mesoscopic, macroscopic level, both for the painting and for the cat. And then you say, what I would really like to get is a file. I would like to get a JPEG file that has the same microscopic structure as a painting and the same mesoscopic and macroscopic texture as the image. So you kind of say that. So you have your descriptors, you create a synthetic set of activation maps for your convolutional neural networks. And then you say, oh, it would be great if I was able to decompress it. So the way you decompress it, unfortunately, it's not so easy. But how it works is that you have your two neural networks, so you compute your activation maps, you create a synthetic set of activation maps. Basically, you compute statistics on those activation maps. And then you say, I'm going to start from random noise, and I'm going to apply my convolutional neural networks and see if the results, the activation maps, look like the one that I want to generate. Obviously, it's not going to look the same, but you're going to be able to compute an error, and you're going to be able to compute a gradient. And so what you can do is you can progressively iterate, you can progressively improve your white noise until it's transformed through the convolutional neural networks, look like the file that you want to obtain. Okay. And this works. Okay, so it works initially. You say that, and you say, "Oh, I'm a bit disappointed," when you say that, because at a microscopic level, it looks like a painting, but you'd like to do something better. But since we understand what we're doing, we can say, "I want to go deeper. I want to have more information about the painting than about the cat," and so that's what you do, and then you get something satisfying. Okay. And the miracle is that it really works, and it's not so hard. Like now, these kind of things, it was brand new in 2016. So those images, they come from actually an MVA project that was done by a friend of mine, who is now at Terapixel, Jaroslav Nikulin, and Roman Novak. So, back in 2016, it was state of the art, very nice. Now it's a tutorial on the PyTorch documentation. Yeah? So that's... it's great. The field has become so mature that these things that were mind-blowing 20 years ago are super standard now. And okay, maybe I should have added a slide, but just to tell you that this idea of generating synthetic activation maps and trying to decompress them by optimizing random Gaussian noise, it's actually very old. And for instance, if you type on Google Portilla Simoncelli, so Portilla Simoncelli, you're going to end up on a web page, I think New York University, of a great paper from 20 years ago, where people were doing that with wavelet coefficients. And you can see that it's not so bad. With wavelets, you're already able to reconstruct some kind of textures. Some of them don't work, but for instance, like oranges, a simple texture, you're able to synthesize it. And so if you see those pictures, if you understand this, you immediately understand that the architecture of the network matters a lot. There's learning involved to make it super sharp, and make it look great. But you should not look at these networks and believe that it's AI and out of nowhere we have gotten what we wanted. No. Those architectures that we are presenting to you, that you are learning about at the MVA, they are the results of decades of research, okay, about what are the algorithmic structures that are well suited to what kind of problem, okay? And so you should not believe that that it's a random architecture, And if you're doing your PhD or if you work in the field, you're going to see that you're going to spend a lot of time designing a good model, okay? So great, it totally works. But then, okay, that's cool. But what we really want to do, especially in medical imaging, is more like doing image classification. Like texture synthesis, it's interesting. Even in medical imaging, you have a CT scan. You say, could I make it look like an MRI? This kind of thing. It can be useful, especially for surgery, real-time surgery. I mean, we can talk about it if you want, but it's useful. But okay, the main application is really, I have my picture. Can I distinguish between a healthy and a sick subject, at a very simple level? So, or looking at natural images, can you distinguish seagulls from pandas? And so what researchers have in mind is they think that, okay, we have here the image, we apply convolutions, 55 different convolutions, so 55 different channels, then 27, 13, 13, 13. Okay, this is an old network. You don't have hundreds of channels. And the intuition that we have, or that we teach, is that in the first layers, you have super microscopic things. And the deeper you go, the more high-level concepts you acquire, like texture, object parts, and object classes. Okay, and this is a dream. But those pictures, they are not very true. Like you should know that that basically, if you take a simple way of generating those images, is like you start from a random Gaussian noise, and you want to optimize the image until essentially it gets very high activation on one channel that you're interested in. And so this is how they generated this picture and this picture. But if you try to do that with the deeper layers, it's not working that well, actually. It doesn't look really good. And maybe if you want to see that, you can go on the blog of Christopher Olah. So you type Christopher and Olah, so O-L-A-H. Interesting guy, lots of blogs, lots of interesting things. And there is a post about understanding deep neural networks. And so it starts with showing you the basic thing and telling you it doesn't work, but we want to make it look fancy. And so he adds a lot of regularization to make it look good. And what it tells you is that, okay, clearly, if you add regularization, you can get object classes to appear one way or another, but it also tells you that it's not out of the box in the network. Okay, those pictures are slightly misleading. And so the deeper layers are not that reliable. So you can think that this architecture that we use is super well tailored to do pattern detection. It does it extremely well, but it doesn't do much more than that. And so maybe this is a bit this is a bit of an extreme statement, but you can think that the microscopic layers, they are very reliable. They do what you expect them to do, but the macroscopic layers, not so much. Okay, and so a paper that was interesting about that, from 2015, so I mean, we've known that for a long time, is how can you fool a trained neural networks? So what are those images? People took, I don't know if it was a ResNet, but a state-of-the-art network for image detection back in the days, and train it on ImageNet, to be able to distinguish between penguins and seagulls. And then they try to optimize, and then they found a way to generate images that would be classified with super high confidence by the network, but that clearly to our human eyes are randomish gibberish. Okay, so here what you see is an image that was classified with very high confidence as a king penguin. This is a starfish, this is a baseball, this is an electric guitar, this is a parrot, this is a peacock, this is a remote control, this is a freight car. when you see these images, I think you need to see them, because when you see that, you understand that, okay, you see that, you understand why the network thought that this was a remote control, and you understand why you saw that it was a baseball and why this was a starfish. But what you see is that the network, at least naturally, acted like a bag of features detectors. Basically, it saw that in many pieces of the image, you had local patches that look like a baseball or that look like a penguin. It didn't really care about the global geometry, the global structure of the image. And so it said 99% confidence, this is a king penguin, this is a baseball. Okay. And so just tell you that this is very mature. Like, so doing this pattern detection thing, doing texture analysis, it's very mature. Doing shape analysis, it's part of my job. This is more difficult, or this is more computationally expensive, and so we are still working on that. It's we are trying to make it mature enough so that in 10 years people would just play on a button. It's going to be a PyTorch tutorial, but right now, not so easy. Okay. So now that I've given to you a few candies about the type of things that we're going to see during the class, maybe I can conclude with 2 slides. First, I want to say that this is a very cross-sectional class with respect to the MVA. I'm trying to give you a geometric perspective on the programs, on the methods that you're going to discover. You know, if you take a very big step back on data sciences, as a geometer, I see 3 steps. First, you have domain-specific observations on a population of n subjects. So maybe I have CT images, MRI images, cognitive scores, blood samples, drug consumption history on the left. And then on the right, I have general machine learning methods for clustering, classification, regression, visualization. And I want to plug the 2 together. And the way people do it usually is that either explicitly or implicitly, they built an n by n matrix of similarities. Actually, one way or another, you are defining a graph, or you are defining an embedding of your subject in some space, and then you are assuming that subjects that are close together should be attributed to the same diagnostic. You know, this kind of thing. But the junction between real data and methods that you learn about in the MVA is very often a similarity structure. And so the objective of the class is to understand those objects, understand those similarity metrics. What are the implicit priors that I reflect? Like, what is the influence of this metric versus this metric? And how can we manipulate these objects efficiently? So today was the introduction. And let's have a sweep across the different lectures, the different weeks of the class. So next week, we're going to start with simple stuff. So vectors, linear models, trees and kernels. So what can you do if I say, when you have if you have your spreadsheet and you say, okay, maybe each row is a vector. Okay, what are the type of priors that you can use? So we're going to say, okay, definitely they are interesting techniques, and especially when you have access to high quality features, this is more than good enough. Okay, so especially like tree models, I don't even know if there is an MVA class about XGBoost, about tree models. But if you talk to anyone in the industry, either in radiomix, like in radiology, or to people in finance, they will tell you, of course, tree models are the baseline. Okay, so I want to spend 30 minutes just showing you what they do, okay, and why they are so good in different settings. But then we're going to say, okay, if you have high quality features, the world is easy. So what do you do when you don't have access to high quality features to describe your patients? And so we are going to expect, so first, what people often come up with, which is graphs. Like, you have a graph, what can you say about it? How should you understand a graph? So it's going to be in 2 steps. First, simple tools like curvature, embeddings, and then more like, I wouldn't say better, but advanced research-like stuff about doing deep learning on graphs. So convolutions, geometry, attention, these kind of things. So this is going to be quite CS-oriented. And the concept that is going to emerge is that when you have discrete objects, but when you have large-scale discrete objects, sometimes it's better to understand it as a continuous object. You know, I think if you have taken classes about functional analysis, these kind of things, you have realized that working in a space of functions, working with continuous objects, empowers you. Maybe it's a bit intimidating because you like to work with vectors, matrices, finite dimensional objects. But it's easier to work with a smooth surface than it is to work with a with a cloud of 10,000 points. And so we are going to talk about curved spaces, but continuous curved spaces, always making a link between the continuous and the discrete. So we're going to talk about manifolds, geodesics, and barycenters, and then about a specific type that has a nice structure, which is a space of probability distributions. We're going to talk about the distances that you can put between probability distributions, like dual, adversarial norms, these kind of things. So these are going to be like the main 5 lectures with small workshops, in the class, or if you can bring your own laptop, probably it's better because you've seen that there aren't that many computers. And you can already see on my webpage the links to the notebooks that we're going to use. All the lab sessions are going to be about getting familiar with basic tools. And so in the last session, I'm going to talk more about the computational aspects of it. I assume that you're not so familiar with it, so that's why I keep it in the last session. Talk about C++, like what happens in the actual memory circuits. This is very important if you want to understand the bottlenecks that constrain all research in the field, and what are the solutions to those bottlenecks. And so there's not going to be a lab session because instead we're going to make a small quiz, and that's going to be it. Okay, so that was it for today. I hope that you enjoyed it at least a little bit, that the accent was not too terrible. And anyway, okay, like I strongly encourage you to go in as many classes as you can in the first week, and then pick, select what you do. Maybe a warning, okay, when I was in the MVA, I only took 4 classes in the first semester, 4 classes in the second semester, and I gave my project for the course on neuroscience very late, and so I got very worried of whether or not I would be able to graduate the MBA, just because I was too cocky about taking few lectures. So take 5 in the first semester, and then you rest easy, okay? And that's it.